Good. How are you guys doing?
Doing great. Okay. We are Team Samad. I am Pawan Kalyani. I am the team captain. Uh, she is Mika Pant, and she is the SECUP lead. And we can start with our review, if that's all right.
Absolutely.
Okay, so here are the components that we have lying around here. So can I show them to you while explaining?
Yes,
Yeah.
please.
Whoever's holding the camera near the pieces needs to turn the microphone on that camera because it's currently muted and we can't hear her description.
Thank you. I was wondering what was going on there.
Yeah. Although it looks like that camera is now frozen.
Yep.
One more second. We'll figure something out.
Sorry about that. So yeah, this is the nose cone that we have. This is carbon fiber layer. So it has around 2 mm of 3D print for the carbon fiber is there on top, and we have an aluminum tip for the nose cone. Right? Our body tubes. Body tubes we have right here. This is GFRP. So these are 5 mm in thickness, the body tubes. These have been made with filament winding. Right? And yeah. Give me that tissue.
So, quick question. So, is the nose cone, is that going to be attached to the airframe,
all
or
right.
is that?
Excuse me, I can't.
Can't hear me. Can you hear me now?
Yeah.
Okay.
I
I was
can.
just asking, is the nose cone being attached to the airframe, or is it going to be ejected as part of deployment?
No, the ejection is from between the body tubes. The nose
Okay.
cone is going to be attached.
Okay. You guys attaching it?
Sorry?
How are you guys attaching it?
Okay, screw it.
Sorry.
The nose cone is going to be screwed in to the upper body.
Okay. So, gotcha. Okay.
Right. Then for the fins, we actually did layup of glass fiber, but most of our glass fiber components have gone into cutting. So that's still with the manufacturer, but we have an example of the plates that we manufactured. So from this, the fins will be cut. So these are around 3 mm in thickness.
Okay.
Right? So, yeah.
Okay. For the coupler between the two body tubes, we have two options as of right now. As you can see over here, this is in-house glass fiber layer. We are here to check the synth properties, do a buckling test on it. So as of right now, in case this fails out, we have a backup option for a metal coupler as well. This is mild seat. We'll be cutting it down to 200 long. And yeah, that's about it. And we'll shift to payload explanation.
Okay, quickly, I had a question going back to the fins. What's your attachment method that you're using for your fins?
Fins, we are designing a fin cant. The same idea that we had last year. It's basically two aluminum rings, one top and one bottom. The bottom one will act as a motor retainer as well, and it will have thin aluminum strips that will be holding the fins in position.
Okay, but you guys don't have that yet. You're still putting that
Uh,
together.
in the process of cutting it, like we have given it in the college labs, we'll be getting it in the next week.
And one I always ask is, you planning on using shear pins on your point?
Yes, we are planning on using M5 shear pins.
Okay.
These are the shear pins that we have. We have tested them in our static with it has worked successfully as of right now. We'll be
Great.
conducting more tests to finalize. We also have M4 shear pins to test out in case these are a bit much. Other than that, we'll be using M4 screws for the entire body with lock nuts. We have kept it uniform as to make the assembly more convenient and faster.
Okay, good. And I'm glad. And you, for sure, I saw in the description you guys have been doing deployment tests, and you're planning on doing that with the shear pins as well.
Yes, we have done a couple of tests. I'll tell you about the recovery as well. One second. Recovery. We have upgraded from last year 3D printed to aluminum this year. As to look into the strength, this is the actual one that will be going on the rocket Agnya, and we have been testing over here. This is the one that we have been testing. These are shock cord holes. We have E-matches coming from the bottom over here, and there is another cup sitting on top of it, a 3D printed cup that will have main ejection charge, and a redundant ejection charge is at the bottom in case the main fails for some reason.
Okay, and those both fire at
Yeah.
with a delay between them.
Yeah. So this is the recovery mechanism. I'll tell you about the tender
Hey,
descent.
guys, before you go any further, is this session being recorded?
Yes, it is being
Okay,
recorded.
good. That's
Yeah,
just
good.
wanted to make sure so we can turn the recording in.
Yeah. All right. Over here we have the tender descender. This is the one we used last year, not the exact one, but the one we had test done over here in college. It worked just fine last year, and we have upgraded that with slightly bigger bolts and more volume, like few minor upgrades from last year, as to compensate for the heavier body. We have tested this as well, and it has worked successfully so far. We'll be conducting a couple of more tests to find out what like how exactly they are working out. Other
Quick
than
question
that,
back on your deployment
Yeah.
setup. Was that, did I
Recording
see
in
you?
progress.
Oh, looks like recording just started. Okay.
Mhm.
The deployment charge cup that you had there, it looked like, does those actually fit together? So you've got like a piston situation that's getting pushed apart?
Oh yeah, see over here, this is the recovery mechanism. Well, like this is the tender descender. Over
Yeah.
here, there are holes for shear pin, and this will be in tension like this, held together by the, what do we say, shock cords on both ends. One end will be connected to the drogue, and the other will be connected to the main parachute. At 1500 feet, the ejection charge will explode, and it will separate into two halves.
Okay, so that's good. I was actually
Mm.
asking about your aluminum charge cups that you had previously. I saw you were kind of putting them together. At first I thought they were just a big old charge cup. Does that actually fit together with the other one where it's like a piston that blows apart, or
Uh,
is that just I didn't know if you were kind of putting them together like that's how they were going to function.
These two close together. I am not able to close them right now.
Okay, so that is how they're functioning though. Okay, that was my question. You just looks like you got a little machining
Yeah.
work there to make them fit better.
Yeah. Yeah.
Cool.
Please tell me.
No, that I was just saying that looks good.
Thank you. These are the eye bolts that we'll be using, M10.
So are you going to be welding those?
No,
Or-
we'll be screwing them in.
Well, I mean, see how the eye bolt is open, where it's
Yeah.
just bent around. Those those can, under extreme recovery events, have a tendency to unbend. So I would recommend either finding ones that are a single piece, so there's not that opening there, or if you have the ability to have somebody weld that closed, just that improves the survivability, I guess, of those.
I think we can weld them, and we'll also look into trying to find one with a closed loop. Welding is a possibility over here, so we'll try looking into it and we'll experiment with it as well. Yeah, over here, these are the shout lines that we'll be using.
Okay. Is that like nylon rope kind of material?
Yes, it's a nylon webbing. Right?
Okay.
So these are around 4 mm in diameter, and we've checked, and they can hold more than enough weight than it is required for the patch.
This is the shock cord that we'll be using. This is also nylon braided. It is 10 mm in diameter, and it has a strength of 17.5 kilonewton.
Okay.
As simulated, it is quite more than the margin that we require. Even though we know that this will be gradual loading and not impact loading, but considering multiple safety factors, this rope will be looking good so far.
Is that similar to what you used last year?
Yes, it is the one that we used last year as well.
Okay.
Okay, I'll be explaining a bit about the avionics section as well. Then I'll hand it over to Krishna, our avionics lead, and he can explain you further regarding that. This is our main avionics bay. Over here, it will be screwed in to the body tube on the all sides or at the top and bottom. It is screwed in together with this point. Over here on three surfaces, we'll be having our own SRAD flight computers and COTS computers. We'll be having our GPS module as well. These are the two battery bays that we have designed that will go inside over here. This is the 18650 battery bay, and this is our 9-volt battery bay. These two will be connected using carbon spars as a single unit, and it will be passed inside.
Okay.
Inside this triangular section.
Gotcha. Okay. Looks like, is that 3D printed or
Yeah, the entire structure is 3D printed.
what material are you using?
ABS.
Oh, cool. Okay.
Yeah, I'll hand it over to Krishna for the avionics section.
Sounds good.
Hello, sir. I'm Krishna, the electronics lead of Team Samad, and I will just present you the SRAT components that are going inside the avionics bay. So, this is our flight computer, our SRAT flight computer, Spark. So, it has basically it will calculate all the parameters required for. It won't be included. It won't be used for the recovery systems. This is just a data collection unit
Okay.
and a telemetry transponder basically. Okay, so we have GPS, we have onboard storage, onboard redundant storage, one in flash, one in SD card. We have 915 megahertz LoRa modules. So we will be having a Yagi antenna at the base station. Base station also we have a custom module that will be receiving the telemetry data. Now, the other sensors that we have is the inertial measurement unit. We have a magnetometer and we have altimeter and every GPS, and we have everything powered by a ESP32. And we will be having two of these. One for redundancy. One will just act as a black box, and other will be a transponder. So we will having both of them on one of the faces. Then we have a SRAD GPS also, GPS tracker that will help in the search and recovery after the landing. So this is just a PCB. It is yet to be populated, but it will be populated soon and we will continue the test.
Okay.
Uh, this is the 915 megahertz Yagi antenna that we will be using at the ground station to receive the telemetry. I will hand. Now I'll present you the thoughts that will be used for recovery. First is the first is RRC3 by Missile Works. So this will be our primary flight computer. Then we have Raven 4 by Featherweight Systems. This will be our secondary flight computer, and it will be programmed with a delay of 2 seconds after apogee. So apogee will be the primary, and this will be the secondary Raven.
Okay.
And for the COTS GPS, we are using again featherweight GPS tracker. So we will receive the telemetry over 9.915 megahertz itself to a receiver that will be connected to Bluetooth, and that will relay the
So have you
information to other vessels.
guys, sorry to interrupt, have you I'm assuming you guys have tested with your different telemetry packages running to make
Yes,
sure
sir.
that they function all on those pretty close bands without any problems?
Yes, sir.
Great.
Everything has been integrated and tested, and everything is working very well.
Excellent.
We also have e-match trigger and continuity test on the SRAD component itself. So this will tap into the e-matches, which is controlled by the COD strike computers, and just on our GUI, it will show us the ejection events or whatever is happening, and the
Okay.
continuity of the e-match if everything is working well.
Great.
That will be it for the avionics pair.
Okay.
Any questions?
So your SRAD altimeter, which is going to be tapped into your deployment charges, is that there's not any chances of that interfering with the actual firing of those
No.
charges or anything like that, right?
No, I use an optocoupler, so it is a fully isolated system.
Perfect.
So we will just be detecting it, and nothing will be hampered.
Great. That sounds great.
Thank you, sir. I will hand it over to Soumitra, our R&D lead, to explain you the payload mechanism.
Okay.
Hello, sir.
Hello.
Hello, sir. I'm Soumitra. I will be presenting you the payload design. So this is our payload design. This year, yes. So for this year's payload design, we are working on a specialized stabilization gimbal control. For this year, we aim for a active stabilization in amidst high forces. So we are going to fit in the 3U CubeSat structured part. It is operated by the PID the control systems, closed control loop. Sorry. We are having various IMUs and various other sensors. We are getting the IMUs, with gimbal angles, and the environmental conditions for performance insights. For the payload, the closed feedback control loop uses AS5600 magnetic encoder and inverse kinematic equations for BLDC motor control.
Okay.
This design offers a technical solution for stabilizing payloads in sounding rockets, ensuring the safety and effectiveness during the flight. So for
So
this,
is it just measuring data, or is it actually stabilizing something inside the payload?
it's actually stabilizing it. We are using two BLDC motors over here. We are using magnetic encoders as well. So we'll get angles from it, and we'll continuously monitor it and actively stabilize it.
Okay, that's cool.
And over to Khyati for the GUI explanation.
Okay.
So I'll be explaining the GUI. Am I audible?
Yes, I can hear you.
So basically, at our ground control station, we have the telemetry that we receive in real time. We try and visualize everything and like display all of the values so that it is easier for us to like see and like monitor everything. And later on, when we get the data from the flight, like from the SD card or from the flash chip, we essentially can plot it. We can also have like a static plot of it or a dynamic plot of it based on the options that we select. So I'll just display it. 1 second. Can I, Mihika, can you enable the screen sharing one option? Just give me a second. Yeah. Is it visible?
Yes.
Now it is.
Yes. So this is our home page. Over here we have all the buttons. This is basically our dashboard. Over here we have all the buttons. Host connect helps us to connect it, and host disconnect helps us disconnect it. If we have the data from the CSV file on our system, from the file upload button, we can essentially plot the same data in real time after receiving it. So let us say I've received everything, and then I want to plot it again in real time. I'll use this one. Data upload is for static uploading of the file. So just I click on it, I select the file, and then I'll just get all the plots and all the details all at once. And the
Okay.
file data export button essentially saves everything at the location that we want it to get saved in. The graphs are like this. So we have made it like this so that we can visualize it better and analyze the trends, because over here we have limited values, right? So in graphs page, we can like monitor the trends properly and like observe everything. Over here, we'll have our map. So the rocket, essentially the latitude, longitude, everything will be displayed here, and we can like monitor as to where the rocket goes and what happens. This is, you cannot see it right now, but like we are also planning to have a 3D model over here so that the orientation of the rocket, we can monitor all of that and see how it goes. The CSV file data, all of the data packets and like in a proper format will be displayed over here so that we can see all of the values over here in one page. And this is the settings page. So sometimes we need things in different units. So we have tried making something so that we can save things in different units and like plot them accordingly. Yeah, this is it.
Great. Okay.
Yes. Any questions?
Nope.
Okay.
Looks
you.
good.
Thank you. Yeah, okay, I'll hand it over to Mihitan.
Hi. Am I audible?
Yes.
Okay, so just a couple of things were left. I think we forgot to show you the parachute that we've made.
Mhm.
So, yeah. This is our rope parachute, right? So this is ripstop nylon, and this was actually 40 feet. And so we kind of found the material to be slightly thinner than we wanted it to be. So we have double stitched it.
Yep. No. Good. That's good.
And this is the main parachute. For this, we got another fiber, fabric. So this is actually 67 GSM. So this was good enough that we could make do with single layer. So yeah.
This is the same material we used last year.
Did you guys also do your
Not the
parachute?
exact same.
Oops.
Sorry?
Sorry, I can't quite hear. I can't quite hear you.
This is the same material we used last year. Not
Okay.
the exact same material, but the same
Fabric
cloth.
is the same.
Fabric.
Gotcha. Okay.
All right. So do you have any other questions that?
Excuse me. Sorry. No, I don't, not on the recovery stuff. Now you guys were there last year, so you know all the ins and outs as far as, you know, don't have energetic materials shipped to the hotel, all that kind of stuff. Do you guys already have your motor, squared away, available? Okay. And then what's your, motor retention situation in your motor mount and that kind of thing?
So as I said, the fin can that we're using, the bottom plate of the fin can will be the inner diameter will be slightly lesser than the outer diameter of the motor casing.
Okay.
So that will also be acting as the retain.
Great. Okay. Well, I think you've touched on pretty much everything.
Greg, can I ask a couple questions real quick?
Please.
Yes.
I saw your tender descender. Is that going to be mounted into the rocket against a hard point, or is that going to be partially out of the rocket as it falls along the shot cord?
It will be outside the rocket. Once a drop parachute opens, this tender descender will be officially outside the body in tension forward.
Okay. How far away from there's going to be an altimeter that is going to energize a wire that's going to fire your tender descender, correct?
Yes.
How far away from the altimeter bay is the tender descender going to be as it's deployed and falling under drogue?
About 2 to 3 meters.
Okay. What I'm worried about is if that wire and your shock cord start spinning around each other, because when rockets are falling under drogue, they like to spin in circles. If the wire and the shock cord are running up parallel to each other and next to each other, they can start winding around each other, and your shock cord is more than strong enough with enough winds that it will snap your wire without any problem at all, and all of a sudden your tender descender is now disconnected from the electronics that would fire it.
Yeah. We'll look into that issue. We have we have missed that point so far.
I can't hear who's speaking. I'm sorry.
Okay. We'll look into that issue. We have missed that point so far. We'll be keeping it just slightly out of the body tube so that it is not tangled out with the top one. If I to fill this out of it.
Greg, are you able to hear his reply? I'm sorry, I can't hear it.
I'm not able to hear it either.
Hello.
There we
I
go.
can hear you.
All right. Okay. So basically what I'm saying is we have not figured that out.
Lost you again. I'm sorry. You keep moving away from the microphone and we stop being able to hear you.
Hello. Am I audible now? All right. Okay. What like we have not exactly looked into that issue, but like what we'll do is we'll keep it to like just slightly outside the body tube so that it does not tangle with the shock cord, because this issue was there last year as well, I'm assuming. And so one second. All right. Like we'll just look into that issue. That does not happen. We'll make sure of that.
Good.
Anything else, sir?
Not for me.
Yeah, that was a good call out. I haven't had a lot of experience with those devices, but I have had experience with very twisted up drogue lines. So yeah. Great. Okay. Well, yeah. Let me see real quick. Do you guys have anything in your nose cone? Is there anything in any batteries, electronics, or is that all in your avionics bay?
Our shoulder will be withholding the payload in such a way that just it will be inside the shoulder section, but not going inside the nose cone.
Okay, so there's nothing, so
That's
nothing in the nose
there
cone.
will be just a bulkhead holding the payload in its position. That's it.
Okay, I'm just walking through the checklist really quick to make sure I don't miss anything. I think I'm going through here. It looks like you guys have covered pretty much everything. You got your motor squared away. Material construction looks good. You covered your payload really well. Yeah, everything looks great. Thank you for your time.
Thank you so much. Do you have any other suggestions for us while you're getting that we need to prepare for anything?
Not from me.
At the moment, nothing more from me, but you guys have my contact information. So if you have any questions or anything between now and the time of the launch, don't hesitate to get a hold of me. And obviously, I'll have your motor and everything with me out in New Mexico when we get there.
Thank you so much.
All right. Thanks, you guys.
Thank you, sir.
Thank you, sir. Have a good day.
You too.
You too.